Welcome back, ladies and gentlemen. In this video I intend to talk about the idea of Schwarzschild black hole. Remember, in the past few videos we talked about the particle dynamics in Schwarzschild spacetime, and that had to do something with the geodesic equations. But this time we'll talk about the spacetime itself, and we'll see how the structure of the spacetime predicts the existence of a black hole at the origin of this coordinate system. So here we have the Schwarzschild metric written in a coordinate system which has four components: t, r, theta, and phi. Of course, d omega squared contains all the angular components, and then we interpret r as the radial coordinate and t as the temporal coordinate. We do know the fact that the metric is a geometric object, and as a geometric object as a whole, the coordinates individually bear no intrinsic meaning. However, we can compare them with the known structure of coordinate system, and we can give them a meaning. So in this case, t has got the meaning of time, whereas r has got the meaning of radial coordinate, and theta and phi have got the meaning of the angular coordinates. But in reality, I'd like to explore beyond the intuitive limits of the coordinate to see what we get mathematically, and then we'll try to impose a physical meaning on the result in the said coordinate. That's the goal here. So in order to understand the Schwarzschild spacetime and the black hole structure, we'll need to understand the coordinates, how to change the coordinates into something meaningful, because there are infinitely many coordinates transformation possible, but not all of them will lead to meaningful physical quantities. So you have to be very careful here. At the same time, we'll have to be comfortable with changing the coordinate system. The particular coordinate system that we have written the Schwarzschild metric in is called the Schwarzschild coordinate. So this set of coordinates, we shall give them a name. They'll be called the Schwarzschild coordinates. When written in this coordinate system, we notice that this coordinate, or the metric written in this coordinate, has got two singularities. Apparently there are two singularities associated with this metric when written in the Schwarzschild coordinate. Let me explain. The first singularity that is readily available for us to see is the point of origin, which we dub as r equal to 0. If you have r equal to 0, then a lot of interesting things happen, but the most notably that this r here goes to 0, and suddenly the four-dimensional space-time collapses into something that we cannot attach a meaning to. There is another source of coordinate. The singularity is the point where we have r equal to twice mu. In that case, this coefficient right here and this coefficient right here gets to 0 or 1 over 0 depending on the type of the coefficient, and that also leads to a type of coordinate singularity as well. Now, of course, we need to understand whether these coordinate singularities are actual singularities in the space-time. Do we have a point or something that is a result of choosing bad coordinates, or there is actually physically something happening there that we need to investigate further, and changing the coordinate to a supposedly good coordinate will not do us any good at that point. If the singularity is removed by a simple coordinate transformation, then of course we have a coordinate singularity. It's not a real singularity, and coordinates are just the construct of imagination. But if we do have a real singularity, then no coordinate transformation is going to change that fact. And we have two candidates in this case. and it's time for us to investigate what is going on at these 2 points. One of the important tests that we can do or perform is to construct quantities that have meaningful physical impact. So for example, curvature. Now curvature is a tricky thing. It's also one of those things which are very hard to calculate. And if you really talk about the curvature tensor, then you have a lot of components to deal with. So for example, R, mu, nu, rho, sigma. This is a representative component of the curvature tensor. And the spacetime curvature is covariantly described by the collection of these components of curvature tensors. But if we do change our coordinate system, these components of the tensors can also change. So what's better for us is to find a quantity which is dependent on the curvature, but which is not a tensor or a tensor component, which will not change with the transformation of coordinates. And that is done by determining the curvature scalars. Now there are lots of curvature scalars, but one in particular in this case comes very handy, which is something called the Kretschmann scalar. So this is defined by multiplying the components of the curvature tensors, but one needs to be such that all the indices are lower indices, and the other needs to be such that all the indices are the upper indices, and then we contract all the indices of one with all the indices of the other. And this is called the Kretschmann scalar. So Kretschmann scalar. We could also find out the curvature scalar, but Kretschmann scalar is a curvature scalar as well, and it is used in many cases. And in this particular case, if we calculate it in the Schwarzschild coordinate, we find out the Kretschmann scalar is given by 48 mu squared divided by r to the power 6. Now, if you notice carefully, plugging in r equal to 2 mu does not do anything significantly different in this case. And the Kretschmann scalar behaves perfectly fine at r equal to twice mu. It's a number. It's a nice regular number. So it gives us the idea that probably the singularity associated with this point r equal to twice mu, or the surface to be precise, is perhaps just a coordinate singularity. However, if we do plug in r equal to 0 in this expression, then indeed we get a singularity. This expression blows up because you cannot plug in 0 in the denominator. So that gives us the idea that probably this thing here, r equal to 0, that particular point, is indeed a singularity in the Schwarzschild spacetime. And that's exactly what is happening there. So our next goal is to create a coordinate transformation which removes this coordinate singularity. And we also know from a previous discussion that no amount of coordinate transformation will remove the coordinate singularity in here, because it's not just a coordinate singularity, it is a singularity in the spacetime, which is evident from this Kretschmann scalar. And the benefit of using this scalar is that it's a scalar. If you change the coordinate, this quantity does not change. Remember, that's the definition of the scalar. Scalars are invariant under the coordinate transformation, where tensor components change covariantly under coordinate transformation. So that's our next job. Our next job is to find out the appropriate coordinate transformations where we can extend our coordinate system and our spacetime beyond the supposed coordinate singularities.